So last time, we talked about authentication, registration and authentication, which is cool and all, but that's not really what we want in our apps. We want login systems. So let's take the extra step to get there. And for that, we're going to need authentication tokens. So last time, from the user perspective, things were pretty straightforward. We're used to this as just users of the internet. You register. When somebody registers, they're going to give us a username and password. We're going to securely store that password. And when somebody wants to authenticate, they're going to give us their username and password. We pull information from the database. We check if the username and password are legit. And if they are authenticated, and that request can be treated as though it were coming from the owner of that account, or at least somebody with access to that account. And this is fine and all, but what happens when somebody actually wants to use our app? Every time we want to authenticate one of their requests, how are we going to authenticate it? And users need to authenticate often. For our apps, for Homework 2, every single time they send a chat message, we need to authenticate who sent that chat message. For any major app out there, anything with like continuous scroll, you're just scrolling through your social media feed. Every time new content is loaded up, that request needs to be authenticated. Then they need to know who you are, and then they need to go to their algorithm and figure out what exactly to send to you, and then serve up that specific data specifically to you, for you. Anything we do needs to be, most of the time on most apps, needs to be authenticated. So authentication happens, can happen multiple times per second when you're visiting a site sometimes. So what do we do when we need to authenticate so many requests? Well, we're going to have the user type in their username and password every single time. Well, no. This is where we're at, though, with just authentication. This is all we really have based on what we talked about on Monday. This is a terrible, terrible idea. Nobody's going to use your site if you do this. You would never use a site that does this. It's just not going to happen. Terrible, terrible user experience. Not an option. Another bad idea is with the mechanisms that we have, with everything we've covered in 3.12 so far, you could come up with this solution. Set the username and password in a cookie or cookies for the user, and now their username and password is automatically sent on every single request that they make. This will work fine. It will work, but their password is now stored in plain text. We don't store passwords in plain text. No, not even client-side. Those passwords should not be stored in plain text anywhere. We're not going to do that. So it's a decent idea that would work. This would function, but it wouldn't be secure enough. It's not going to meet our security standards. And our users are going to be compromised. Passwords are going to be leaked. Things are going to go downhill with this one. So we don't want to do that. We need a new idea, and that's where authentication tokens are going to come in. Authentication tokens are when somebody logs, it is login at this point, but when somebody authenticates, we're going to issue an authentication token. This is a big random token that we're going to assign to that user. We're going to associate it with that user. And I use that word quite a bit in the homework handouts especially. We're going to associate this value with a user. What I mean by that is we're going to put that in our database and remember whose that is. So we can either create a separate table or collection where we store tokens and usernames and associate them that way. Or more preferably, and easier I should say, is go to that user's account that already exists. Wherever you're storing username and salted hash of their password and the salt, go to that and update it with their auth token as well to add that token to that user's account. Easier. The first way is probably preferable when I think about it, but the second way, it's going to be a little easier to build. And then we're going to set that token as a cookie for that user. And now every single time we get a request from this user, it's going to contain their authentication token. We're going to look up that token in our database, see who it's associated with, and then treat that request as authenticated from that user. So we're authenticating with their username and password one time, issuing an auth token, and then whenever we see that auth token, we're going to treat that as an authenticated request coming from the user associated with that token. And this is how we want to build our authentication systems. And now we have an actual login system. Once that auth token is set in the cookie, and store it in the database, we have a true login system. Instead of authenticating, users are logging in, and then the auth token is doing the authentication for them without having to provide their username and password every single time. And this is what we like. This is what we use out there on the internet. When we're using the internet, we have all these auth tokens set as cookies. Some sites don't use cookies specifically for this. They'll use local storage and some other mechanisms. What other mechanisms? Just local storage. What else would they do? Use local storage instead of cookies, and then have custom JavaScript that'll pull from local storage and then attach that token to request, basically rebuilding what cookies do for us already. Anyway, they're going to store an auth token on the client side and then have that token sent on requests, on every single request. I don't require this on the homework, mostly because it's a pain to test. But you should have these tokens expire at some point. I just say as long as they expire, as long as they're not session cookies, I'm fine with it for the homework. I would like to say some requirement, like they should expire in a year or something, but that's hard to test once timing's involved. So, so I'm not going to require that. But what you should do is when the tokens expire, don't just have it expire on the cookie side, also have it expire on the server. When a token should be invalidated, your server has to mark that as invalid, which is what makes it hard to test. We could just look at the timestamps on the expiration of the cookie, that's fine, but that's front-end security, and front-end security, the one thing you need to know about it is it doesn't exist. There is no security on the front end. A user can just change that timestamp. Everybody can just mess with that. Can't trust anything client-side. Don't trust your clients. Don't trust your users. But we have to invalidate that server side, and grading that would be a pain. We could say your tokens have to expire in 30 seconds, but then testing your functionality, did I take more than 30 seconds and now my token's invalid? Or, it just it's a pain, it's painful anyway. So you should do this. There's quite a few points in this course where I say this. You should do this. When I say that, I mean, in practice, please do this, but I'm not going to grade it on the homework or project. But you should invalidate the tokens at some point. You have to have some expiration time that you choose when you set the cookie. If you look at your auth tokens for real-world apps, some of them are expires in the year 2040 or something like that. They just expire in some ridiculous time in the future, which is fine too. Yep. Either way, and I will talk about that in later slides, so I'll talk about it right now. Invalidating a token, either delete it from the database or mark it as invalid. Based on our soft delete conversation from before, I prefer marking it as invalidated. For this course, if you're deleting them, it's whatever, I don't care. Out there in practice, you might want to invalidate them without deleting them, just in case having that record of the history of all their past logins, maybe that helps you debug a bug sometime in the future. Okay, and I think I want to say right here is this seems exactly like, so whenever we see that token, we authenticate them based on that token. Based on possession of this token, that's how we authenticate them, because we only issued this token to one specific person. If they have that token, they must be that person. There's no other option. That's how our server is going to behave. Whether that's actually the truth or not, but that's how our server is going to behave. So this sounds just like our terrible idea from a few slides ago. If we're storing these tokens and saying, if you have this token, you're this person, isn't that the same as just storing their username and password in a cookie? And it is very similar. These things are about as powerful as username and password. So it doesn't seem like we got too far. The big difference here, and I don't have a slide for this one, I just want to talk about it here. The big difference here is revocability. If a token is compromised, it kind of goes with what we were just talking about too. If a token is compromised, you invalidate the token, user sends their username and password again, gets issued a new token, done deal. That attacker who stole the token can't do anything anymore. If an attacker steals your password, Now the user has to reset their password. They have to remember a new password. It's a much worse user experience when a password is compromised and revoked than if a token is compromised and revoked. Plus tokens, we can set the expiration. If it's like a banking app where our users aren't going to mind typing in their username and password each time, is just how, what are we going to not access our money anymore? The banks can do that. So for extra security, they're going to have our tokens expire pretty quickly. And then if somebody does compromise a token, there's not much they can do with it because it's probably expired by the time they possess it. Password, not so much. Password's a much more painful thing to have compromised. So that's the big difference between auth tokens and passwords in cookies. Don't ever put a password in a cookie. All right, so these things need to be very high entropy random values. I like the 80-bit rule of thumb. As long as you have 80 bits of entropy, we're feeling pretty good about that. But there's really no harm in going up. Like, why not just make them bigger? You can go way higher than 80 and just have solid security. You get 200 bits of entropy. There's not much harm, just some storage space. Not much harm in going bigger than this. But at least 2 to the 80 unique tokens, that's a big enough number that an attacker's not going to randomly guess one of these. This is because we want that reasonable assurance. You possess this token, you must be the person that authenticated with the username and password at some point in the past, because I only gave this token to that person. So if you have this, you must be that person, or potentially somebody stole the token from them. It can always happen. But we're going to be reasonably assured that somebody didn't just guess that token. And this gets, somebody doesn't have to just guess your token. If somebody's trying to attack an app, they're going to go to their cookie, and they're going to just guess any random value. If that value matches the token of any logged in user, then they are that user. They're effectively that user, because that's all the server's looking at is, do you have that token? If you have that token, you're that user. So if there's an app with millions, or for the major apps out there, possibly even billions of currently active logged in sessions, and you have tokens with pretty low entropy, they're just going to guess any random value and eventually hit a valid logged in authenticated session, and they're going to hijack that person's session and be that person. 2 to the 80 is a freaking huge number, to the point where even if you have billions of people logged in, that attacker is never going to randomly guess an actual valid token. Bless you. With high probability, I always had to put that clause in there. Of course, it's all statistics, it's probability. They could just by pure chance on their first guess get your specific token, but it's so unlikely that we're comfortable saying that's just not going to happen. Okay. We generate a token, we set it as a cookie, and we need to store this in the database. We're going to store this in the database so we can look up the user. And this is where our conversation is going to take a turn like it did last time, and we have to talk about how we're going to secure these things. We have very sensitive information here that we're storing in a database. So if we store all these tokens in a database and somebody compromises that database, they take any one of those tokens, they set it as their cookie, and they are that person. They just hijack that session. So this is a very lucrative target. I say in the slide as lucrative, as sensitive as passwords. It's a little less because of the revocability of these tokens, but it's still a very lucrative target for an attacker if they get all these tokens. So we have to securely store these things. And it's a little bit different than storing passwords, but a lot of similarities. So let's talk about them. The similarities, we're only going to store hashes of these tokens. And there's a key distinction. I'll say this multiple times today and make sure we're all on the same page. I had quite a few zeros I'd say quite a few, it was maybe like 5 zeros last semester of students messing this one up. We're going to store hashes of these tokens in the database, only the hash. And the token that we set as the cookie is the plain text token, the unhashed version of that token. Do not set the cookie to the hash of that token, because that completely defeats the purpose of hashing. So with that, let's talk about what the purpose of hashing is if somebody compromises the database, they get a hash of the token, and they can't reverse that hash. They can't undo the hash. So they're resorting to the attacks that we talked about last time. They can try to brute force it. They don't have a dictionary attack here because we're using code randomly generating these bits. They're not going to be able to perform any dictionary attack, and they can launch a rainbow table attack, but when you have 80 bits of entropy, that's too much entropy for any rainbow table to ever overcome. Even rainbow tables are completely useless once your entropy is that high. Our passwords never have entropy that high. Unless you're using a password manager. You can get as much entropy as you want. It's effectively the same thing as generating these tokens. But since the entropy is so high, rainbow tables are useless, which means we don't have to salt. If you are the paranoid variety and you want to salt your token hashes, I'm not going to stop you, but I'll give you this warning is that it's a lot more painful. The database lookups are going to be a lot more painful to do. It's going to be a lot more code you have to write. And you get no security gain, no perceivable security gain because your token's already had tons of entropy. If you don't like how much entropy your token has, just generate bigger tokens. It's not that big of a deal. And I do, before somebody asks, I do allow the secrets library to generate these tokens. However you want to generate your big random tokens, it's fine. Secrets library is probably the best, fastest, easiest way to do that. And getting more entropy is a matter of replacing one int with a bigger int. Like if you're ever thinking of hashing these things, just increase the size of that int. If you're generating 256-bit random random tokens, and then you're like, well, I want to store hashes of these to make them even more secure. Well, your value is already at 256 random bits, and then you're going to hash it. If you're using SHA-256, it's giving you a 256-bit hash. You're effectively getting the same thing. You have the same amount of entropy, the same everything. The attacker doesn't care if they're looking at this 256 random bits or this 256 random bits. You effectively have the same thing. You have the same entropy, the same security. Everything's the same. With the salting. I was talking about salting there. I was thinking of a question that was asked in the other lecture. Why not hash and set the cookies to the hash, and then in the database store a hash of the token, and it's because it doesn't get you anywhere. Just create bigger tokens. You don't actually gain anything. It's not like passwords where we have to know that users are going to have weak passwords, and we're trying to get rid of the rainbow tables by salting those things. Not the same thing here, because the entropy is so high that the rainbow tables are useless. Okay, so we're only going to store hashes of the tokens and then set the cookie to the plain text token. If I kind of lost my sense there. Well, if an attacker compromises this database, they have hashes. They can't break those hashes, so they don't know what to set the cookie to. That's just useless information that they have. But if you hash and then set the cookie to the hash of the token and store a hash of the token in the database, what they get from the database is the same exact thing that you're expecting in that cookie. So they take the hash from the database, set the hash to the cookie, and now they hijack the session. And sure, you hashed, but since you hashed both values, it was completely pointless. So don't do that. It will be a 0 on the objective. Like I don't know if that sounds like a nitpick or not, but when you do that, it shows that you don't understand why we're hashing at all. So it is a vulnerability, so it's a 0, but it also demonstrates a complete lack of understanding of hashing, so it's definitely a 0. It's not a BS 0. It's you didn't learn what you're supposed to learn 0, unfortunately. Okay, I think I've talked about that enough. Plus, I'm going to mention that again later too, because it's so important. And with these, now that we have authentication, we want to verify the user. We're going to verify that the user is who they say they are based on that token. And if they're not, we have our 400-level response codes based on authentication. We have 2 of these. I only talk about 403 in the homework. I don't have anywhere, I don't think anyway, where I added that you need a 401 response. Maybe I did. I don't think I did, though. But a 401 and 403, these are our 2 most common response codes based on authentication. 401 means the user's not logged in. You're unauthorized to access this protected resource. You need to be logged in to be able to access this. So this means they either sent us a request with no token at all, the cookie wasn't set, so they're just flat out not logged in, or the token in the cookie, it was not associated with any user account. Maybe it's a token that's been revoked or whatever. But whatever the case, we can't verify this request to be belonging to a specific user or in a specific account. 403 is similar. This means you are logged in. We know who you are, and you're trying to access something that you're not allowed to access. So we got the token, we looked up who the user is, we got their username, we know the account, and they're trying to access somebody else's DMs, for example. We're going to send them a 403 and say, hey, you're not allowed to do that. And none of these checks can be front end. I hope this one is self-explanatory. I added it to the slide, and it got way too much text on the slide because of it, too. But and hopefully I don't even need this, but never do any of these checks client side. There is sometimes a temptation to have your endpoints just serve up all the data and then have some code on the front end that says, well, since it's this user, they're not allowed to access this data, so we're going to filter that out on the client side. We know not to do that because a user is just going to look at the response from the server directly, not what they are viewing through your front end. They'll look at the raw response, see all the sensitive data, no good. These filters and checks have to be done server side so that no sensitive data ever leaves your server without being verified that the person you're sending it to is allowed to access that data. And then logging out. When somebody logs out, you are to invalidate that token. Whatever token they have, they send a logout request, you look at the token in their cookie, pull their account and whatever, all that good stuff. And then in your database, you either delete that token or mark it as invalid. Whatever you do for this, the mechanics is up to you. The mechanics are up to you. But whatever you do, if you get another request with that token, it needs to not be valid. It needs to not be validated. The concern here is if somebody does hijack a token, or even if your user just thinks that there might be a chance that somebody hijacked their token, then they want to hit the logout button, invalidate that token, and then whoever hijacked that token, they can't log in anymore. Since that token is now invalid, that hijacker who stole that cookie can't do anything with it, and then the legitimate user sends their username and password again, gets another auth token, and now they can continue using the app. They don't have to reset their password or anything. So when you log out, don't just delete the cookie. You should delete the cookie too. This is another case where it's not part of the requirements of the assignment. I don't know why I didn't make this one part of the requirements. That one's easy enough to do. But to delete a cookie, you set the cookie again with an expires that's in the past using the expires directive. As a timestamp that's in the past, and the browser is supposed to delete that cookie. Don't just do that. That's not logging out because that token is still valid, and if the token was hijacked, the attacker still has access to the account. That's no good. We don't want to do that. So don't just delete the cookie. You should delete the cookie anyway, but we like server-side protection, not client-side protection in this class, or actually ever. That is not just a 312 thing. But we need server-side protection. Log them out server-side by modifying your database and revoking that token. Okay, any questions on all of that? My next thing is going to be some diagrams. I got through all the theory, all the concepts, all the content is out there to do everything you need with authentication. We're up to LO2 on homework 2 at this point for reference. And Friday is going to cover LO3, and then next week is AOs only. So we're almost done with learning objective content for homework 2. So any questions here? The rest is a diagram and examples going over what we've talked about the last 2 lectures. So any questions at this point? Y'all are quiet in chat. I had to check to make sure I wasn't on the wrong Wi-Fi again. Got to be questions out there, though. If not, I'll be happy to just keep charging forward. Not even questions on homework 1. Got our first deadline coming up Monday. Charge on forward. Let's take a look at the whole process here. I want to go over everything on Monday, everything we did today, and just kind of walk through and visualize what it all is, because a lot of it I covered with bullet points, and it's not 100% clear. So let's talk about how the interactions actually look when a user is logging in. And I'll keep an eye in chat if somebody wants to ask. Okay. Very first thing, somebody registers a new account. They're going to ship username and password to us. And they're going to say, this is an account that I want created. It's all the user needs to provide is those two values. We get these two values, and we're going to generate a random salt. So this is one just big, long, high entropy random value. Doesn't add entropy to the password itself, but it does have entropy in that an attacker can't easily guess what the salt is going to be until they compromise the database. Or else they would build rainbow tables for a specific salt if they know who they want to attack. So we generate a random salt. We append the salt to the end of the password that they gave us. So we have the password that they gave us. Then we appended that salt to the end of it and took a hash of that value and got our salted hashed password. So a salted hash of the password that the user gave us. And we're going to store all this information in our database. We go to our database and we say, this is the user's record. Here's the random salt. It is stored in plain text in the database because it has to be, because we need that salt during verification. When somebody wants to attempt to authenticate as someone, to authenticate them, we need that salt. So it's stored in plain text and the salted hash as well. Those are the three values that we're going to store in our database. If you're using bcrypt, which you should use bcrypt, just use bcrypt, please. Actually, not please. I don't care. But it'll save you a ton of time. If you're trying to build your own authentication system from scratch, it's a lot of work. With bcrypt, it is 3 method calls. That's it. 3 method calls. So bcrypt has a generate salt method, and it has a hash method that'll take a salt and the plain text password that you want to hash, and it'll return one value. So for practical purposes, on your homework and on your projects, use bcrypt. I mean, bcrypt's industry standard. Let's just use this one. We don't have to homebrew our own hashing algorithms and everything. Use what they've built in bcrypt. They have all the latest countermeasures and anything in there. Much more secure than anything you'll homebrew. And that's going to spit out one value. You say, bcrypt, hash this password with this salt that bcrypt just generated, and it gives you one value that looks something like this. And this value has the salt and hash all rolled into it, plus some meta information that says how many bytes of this, or how many bits of this is the salt, and how many bits of this is the hash itself. So it reads effectively the headers here, and then pulls the salt and hash out of it, and then does its thing after that. It'll call the third method. That was only 2 of the methods. The third one is a user gives us another plain text password. We pull this one single value out of the database and give check password both of those values, and it'll do all the work. It'll take the salted hash, extract the salt, append it to the plain text password, hash that, and check the hashes. It'll do all that, so you don't even have to be worrying about the minute details of how it's going to handle all that. But you do need to make sure you have a salted hash stored in your database. For the rest of my example, I'm going to split the salt and hash because I want to show you the theory of what is actually happening, not a library-specific implementation of how to do this. So I'm going to split them up again. So now a user already registered, and this is what we're storing in the database for that user. And our database will, of course, have everybody's user account. We'll have these 3 values for all the accounts that have been registered. And a user wants to log in. To log in, they're going to give us username and password, and ideally the same username and password that they registered with. We take these values. We're going to take this username. When a user sends us username and password to log in, what they're saying is, I claim to be this user, and here's my password to prove it. So we're going to say, all right, you're claiming to be this user. Let me pull the information out of my database for this specific user. So we're going to get that record for this user, and that's going to pull from the database the username, of course, but we already had that, but importantly, the salt and the salted hash. So we get these two values out of the database, and now we have everything we need for verification. We have the username that they're claiming to be, the password that they're submitting for their login attempt, the salt that we're going to append to that password, and the salted hash that we're going to use to verify that password that they provided. This is everything we need. We're going to take the salt, append it to the end of the password attempt, hash it. We get this hash, and we're going to check to make sure that exactly matches the hash that we pulled, the salted hash that we pulled from the database. If they exactly match, authenticated. If they don't exactly match, bit for bit, not authenticated. No good. If your password is off by a single character, so instead of the @ symbol, we have a lowercase a here, just one symbol, or even if your password, hash functions in general, cryptographic hash functions in general, if the input is off by 1 bit, there's 1 bit difference from the expected, from 2 different inputs, the hashes will be completely different. So my password is almost right, but the hash is completely different than the expected hash. This is a property of cryptographic hash functions we didn't talk about, but a very important one is that even if the inputs are very close, the outputs will be very different. And to put this in more mathematical terms, if there's even 1 bit difference in the inputs, the outputs, every single bit of the output will be different with probability 50%. So every single bit will effectively, to us, it won't be literally random, but effectively to us will look completely random, completely different with a 1 bit difference in the input. This is why when we're talking about attacks, we didn't talk about any attacks like, well, if the user's close, the attacker's close, then the hashes will be close, so we'll use that as information and build some hill climbing algorithm that gets closer and closer to the right solution. We can't do that because even if we're so close, off by 1 bit, we get no information from that, and that's the way we like it. So even if you type your password wrong by just a little bit, and you're like, man, just let me in, I was so close, like, no, we can't do that because in our code that's authenticating you, we saw 2 hashes that are completely different. We don't know that your input was so close to your actual password. Nobody actually knows, and that's the way we like it. We don't want to leak information about your password at all. It's either an exact match, 100% exactly the password you registered with, or it's not. That's the only information we get. It could be off by 1 bit. It could be completely someone else's password completely. It could be an entirely different string. We don't know. We just know that the hashes were not identical. But if you give us the same exact password, the hashes will be bit for bit identical, 100% identical. So only if the hashes are identical do we want to accept that new password, that login password. And then once they're authenticated during the login process, we generate a random auth token that should have at least 80 bits of entropy, but more is always better and easy enough to just increase an int, as we mentioned before. And then what we store in the database, when we update this user's record, we're going to store a hash of this token. The hash of the token that we're storing, but the plain text token that we're setting as their cookie. Very important. I already said this once, and I'm going to say it again right here, just to make sure nobody who shows up to class and pays attention makes this mistake. So I'm going to make assumptions when people make this mistake. Hopefully nobody does. I would like to see nobody make this mistake, to be honest. But we're going to set the cookie to the plain text token, and what's stored in the database is a hash of that token. So if someone compromises this database, they get the hash of the auth token, and they have no reasonable attack to go from this hash to the value that our server is expecting as the value for that cookie. If the cookie was a hash of the token, and we stored this value here in the database, and also set that value as the cookie, somebody compromises this database, grabs this value, sets that value as their own cookie, sends a request, and they're authenticated because that's the value that our server is expecting. But instead, our server is expecting this value, server gets this value, hashes it, and checks if the hash matches. An attacker who gains access to this hash basically has a garbage value. It doesn't do anything for them. There's nothing they can do with this hash. What they can do is try to attack this password, because the password is going to have much, much significantly less entropy than the token, unless somebody's using password manager. I always have to put that asterisk on things. They're going to attack this password because they're not going to get anywhere with this hash. If they're capable of breaking this hash, they can break this one trivially. If they're that sophisticated of an attacker who broke hashing algorithms and didn't tell anybody and is just out there wreaking havoc, they're going to crack the password first before they're ever going to crack something, a hash of something with more than 80 bits of entropy. It's just not going to happen. Are security questions for password resets stored similarly? No. Bless you. No. Something similar came up in the other lecture, so I'll go off on a little tangent here to talk about that. We store hashes, we store passwords like this, we store auth tokens like this with hashes and hashing, and you know what else we store using hashing like this? Pretty much nothing. This is about it. Like that's how we use hashing to secure things. What these two values have in common, what properties the passwords and these auth tokens have in common, is that our code never needs to produce the raw input again. Our code never needs to know what the password is, and our code never needs to know what that auth token is, ever again. Both of those values are provided to us by the user. We never need that information again. We get it from the user, we do our hashing and or salting, and then check if the hashes match. That's our use case. It's a one-way function with information given to us by the user. In the case of an auth token, it's a value we gave them, and then we throw away that data, and then we just rely on them providing us that information again, hash it and check the hashes, and then throw away the plain text again. We never have to go to the database, look at either one of these hashes, and figure out what's being stored like this. With a password hint, we do need that information again. If somebody asks us for the password hint, whatever we store in the database, we have to take that information and generate their actual password hints and then send that to them. So those password hints cannot be stored securely. They would have to be stored right alongside your information here. So an attacker compromising the database would have your password hints as well. Those have to be stored, I don't want to say insecurely, but they can't be protected as strongly as these values. They can't be hashed like that because hashes are one-way functions. It implies that we never have to go backwards. Same applies to credit card information, social security information, any banking information, any sensitive information where our server needs to know what that information is can't be secured with hashing. So if you store your credit card, you say, save this credit card for future use, that credit card, careful how we word this, that credit card can potentially be compromised if there is a compromise on that server. And this is why you see headlines, when you see headlines of data breaches, the headline's going to read like millions of people's credit card information leaked, millions of people's social securities or any sensitive personal information, home addresses, any PII. That's what the headline's going to read. You'll never see a headline. Well, I hope you'll never see a headline. We better never see a headline like this. There should never be a headline that says millions of users' passwords leaked, because we can secure passwords, and any competent dev with lots of users, enough users to make headlines on a data breach, should be securely storing their passwords. But the rest of the stuff can't be securely stored, including password hints, credit card information, can't be securely stored. What they can do, what a dev can do, is encrypt it and then store it encrypted. But if you're storing it encrypted, in the case of password hints and credit cards and all this sensitive information, you need, in your code, you need a way to decrypt and send that information to MasterCard, Visa, the user, wherever it's going. We need to get back to the original data. And we're not going to do that manually. You can't have like someone with a literal key, a human being that every time somebody wants to get their password hint, we're going to unlock a vault. And we can't do that. We're going to have software that does this for us and automates the whole process. So we have software that grabs the encryption keys and decrypts and then sends it. So anybody with access, with the know-how to be able to compromise your database, your encryption key has to be sitting right next to that database, and they can probably grab that too and decrypt the thing. So it's not nearly as secure as storing hashes. It's a deterrent. Yeah, you store encrypted stuff, it's a deterrent. It does take a performance hit too, for what it's worth. But if you think you can secure that key, but that your database is being compromised, like you probably can't. You can secure both or neither, usually. So storing encrypted information doesn't really help. Hashing doesn't work, so it's effectively insecure storage. So database breaches will get all your personal information. Yeah, the headlines might read password leaked anyway because the journalists aren't always. I don't want to finish that sentence. You can have your own assumptions. They actually, I will finish that one. The clicks are valuable. You know, they're doing their job. They gotta generate traffic. On a government website, once click forgot password, and they sent me a plain text password to me. They're the only people who can get away with that too, because what are you going to do? Switch governments? I mean, some people do, I guess, but they can get away with a lot of insecure stuff. And for what it's worth, the government can spend ridiculous amounts of money securing their databases themselves. So even if they have a plain text password database, they have a lot of measures to protect that database as well. They're not a company who's got to be chasing that bottom line, and they're going to be tempted to cut security measures. They don't have to. They can just glob on all the security measures they want because they have a lot of money. All right. Okay, I think I finished what I wanted to say there, right? Yeah, these are like the only two things we're going to store. Anything that we never need the original value of, we never need to compute the original value of, can be secured with a hash. Everything else is basically vulnerable to a database leak. Okay, back to our diagram. User has this cookie set. Every single request that they make now is going to have that cookie associated with it. And when we get a request from them, we read the cookies. We grab this auth token, we hash it, we check if the hashes match, I'm skipping steps here. We can't just check if the hashes match. We're going to look up in our database any record that has this as their hashed token, and then pull any records with that value. If there is a record, there should only be one or zero. If there is a record, then we pull that record, and now we have all the information, including, most importantly, their username. This user is now authenticated. We can verify that they are this person because they possessed a token that hashed to this value. If you're tempted to salt your auth token hashes, first of all, I recommend not doing that because it's silly. But if you are tempted to, this step is a lot harder. You can't just look up in your database, give me all the records with this hash for this value. What you have to do instead is pull all the records. For each record, grab the salt, append the salt hash, and then check if the hash matches. You're basically doing a password verification on every single record. When it was a password and you were logging in, you had the username already, and you just pull based on that username. But when all we have is the token, subsequent requests for a logged-in user only has the token. That's the one value that you have to work with. And if you're storing salted tokens, you have to go through every record. How do you know what record to pull? You don't. Nobody's claiming to be somebody at this point. That's only during login. They're not claiming to be anyone. They're just like, here's my token. Figure it out. So if you're salting, there's a lot more work to do at this step. than just a lookup. Hey, give me any record with this hash for their auth token. In this case, we did find the record, and we have their username. So this request is verified to be from this user, and we can send them their private data. We can treat their chat messages as coming from them, add their username to it. We just treat this request as coming from this user because they are verified through our login system. Is it impossible to reverse the hash? We talked about it a bit on Monday. I'll say no. Impossible is a strong word, but if you're doing everything right, it should take way too long to be feasible. Like everybody, by the time they break it, they'll be dead. They'll die of old age first. And these cookies are sensitive, not to be grim there. I was trying to reword that to be more positive, but when it takes 1 million years to crack a hash, it's effectively impossible. If there's enough entropy. So these cookies are sensitive. If somebody steals your cookies, they have your login. They have your account. They don't even need your password. They steal your cookie. They set their cookie to that value, and they go to that page, and they are you. They're authenticated as you. All the server's doing is looking at that cookie, or that token. If somebody else has that token, they are you from that server's perspective. Let's do that. So here I am. I'm at Congregate. I'm logged in as me. I'll refresh. Hopefully the Wi-Fi will play nice with me here. Hey, we have some nice Wi-Fi right now. So I'm logged in as my account, and I don't think I showed this in lecture. Maybe I did. But I'm going to the Application tab in my browser console, going to Cookies, and I can see all of my cookies for this website. I have another window. This is a Chrome window. I am not logged in. I'll refresh to verify. I am not logged in. I can go to my cookies and clear them all, refresh, and it'll populate all these cookies. That's how much tracking, how much tracking they're doing of even an unauthenticated, not logged in user. There's a lot of information they're keeping track of here. But what I can do is go through, and I've done this beforehand. I know exactly what tokens, what cookies to grab here. So if you're doing this for some other site, it takes a little bit of work to figure out what exact cookies you want to get. But this Congregate session, this is keeping track of my session. I almost put this on the homework too. Maybe I should have. Is to track guest accounts and guest sessions. With a 24-inch but come and explore it. Oh, let's track a time there. To track guest sessions, let me just do this. So I'll have this token, Congregate session, paste. Oh my God, come on. Work with me. You gotta be kidding me. You don't have to click at it. And I'm going to grab this other cookie that doesn't exist, this Kong sec. It doesn't exist over here, so I'll create it. Set my value. Oops. Oh my God. Come on. And refresh. And without any username and password, I'm logged in as me. All I did was hijack my cookies, get them in this other browser, and I am me. No need to compromise any passwords. You can just steal those tokens. Don't do that at home.